Great. Good morning, everyone. Thank you for joining. I'm a PhD student at Stellantis, and we'd like to share a new approach on how we could extend the current in-vehicle capabilities to enable more flexibility with dynamic updates, new features, and so on, while we, of course, also respect the onboard constraints, such as safety, real-time communications, and so on. So I'll give a quick agenda. I'll go over an introduction on the future automotive use cases. We'll see that there's a real need for dynamic onboard reconfigurations. And so we'll see what it is, how we can formulate it. And then we'll go over our methodology with, of course, some results and discussions. Okay, so here is where automotive is today. We're seeing a lot of new features coming, such as connected services, automated driving. And so you can see that the black curve shows that the number of functions on board is constantly increasing. And currently, this is due to main transformations, the first one being sustainability with shared vehicles, robotaxis, lighter platforms, and so on, as well as user experience with connectivity, subscriptions, and updates. However, you can see from time to time that the black curve flattens out, and this is actually due to the integration complexity, which increases even more when we stay on one fixed onboard architecture. And so this is why we saw CAN buses in the 90s, which brought the complexity back down to enable new use cases. And so today it's the same thing. We're seeing new architectures with zonal architectures to enable more connected and dynamic use cases. So here's an overview of what this looks like. On the left, you have the transition that's happening in automotive. On the left, you have traditional architectures, which are domain-oriented. So you have CAN buses that are separated by domain function domains. And then on the right, you have zonal-oriented, which is kind of the new transition where you have centralized computing resources. And also you share Ethernet networks that are going to share different functions and network flows to limit the size, weight, and complexity of the hardware. So that's good. But at the same time, you have new use cases that are coming in. And so here are some examples to show you that really we have applications, background services that are on different dynamic levels. So if I take the example of vehicle platforms, you have battery management, motor control, which don't change very often. But then in the same vehicle, of course, you might have user applications with infotainment, as well as cooperative services, which might change potentially every second depending on the road environment, as you are all working on V2X. And so this shows that we need to share functions with very diverse resources inside shared resources. And traditionally, the way we do it is today is that we specify what I call configurations, and configurations specify what resources are allocated. So this could be where an application is installed, but it's also when you have traffic shaping rules inside the network. So when packets can pass to respect all the latency and jitter requirements. And so what we envision, what would be really great to have is sort of a hybrid system where you have configurations that specify each application, for example. And what would be really great would be to add them up and change them at the different frequencies depending on the use cases and applications. And with that, this really what drives the need for dynamic reconfigurations so that we can adapt with these new applications, install new updates, new versions, and so on, dynamically while the vehicle is being used. And actually, my talk here is the kind of a second part of a first talk we had on IEEE Standards Association. So if you're more interested on the architecture side of all of this, then I invite you to watch the first part that's available on YouTube on the IEEE's channel. Great. So we have one objective to achieve all of this and to enable it. What would be really great is that an automotive OEM with hundreds of vehicle models and hardware platforms, if they had a unique app store, which includes background services, and then we distribute them and install them on vehicles with the correct configurations to allocate the resources. So that's the objective. But then at the same time, there are constraints. The first one being the heterogeneous fleet that OEMs have. And the second one is also scheduling time, because when you want to generate one configuration for a specific setup, then it takes a lot of time and computing resources, and you cannot do it on board. So we have to find a solution. So on the left, you have traditional methods, what we're doing today. It's very simple. It's completely static. So engineering and marketing teams, they come up with a set of use cases in the vehicle. Then they prepare the worst case of every application active at the same time. And they generate one single schedule to allocate all the resources. and then they install it on at manufacturing time, and then nothing changes anymore. You cannot update the vehicle. You can maybe reflash the software, but it takes time and it's quite cumbersome to do. And so one idea we'd like to explore is to do the opposite. So we break up the configurations into multiple smaller configurations, and this will be dependent on the dynamic use cases of the vehicle. And our main assumption is that all applications will not be active at the same time. So if we take an example, Spotify and Netflix, you probably don't run them at the same time. So you can allocate one common resources for all applications that don't run at the same time. And then so you can dynamically switch in the vehicle. And finally, if you have updates, you can ask the cloud to generate new schedules or to have pre-computed schedules and go up with what's your new state. So here's the methodology we used. To enable this, we introduce a new concept that automotive OEMs don't use yet. We introduce this concept of a vehicle state graph. So here you have a description of combinations of applications that might be active at the same time. So one corresponds to Spotify, the other to Netflix. And then we also model with edge transitions the probability from going from one state to the other, depending on observed states and so on. And so this graph can be generated through several methods, through engineering, marketing teams, just as before, but also simulation with cooperative services and tests, as well as real-life feedback that comes from the existing vehicles, and we can improve iteratively with new data that we get. But I won't go too much into detail for that. However, we can see one problem from this is that, okay, it's great to have a vehicle graph, but then at the same time, if we have thousands of available applications in one app store, then you might have tens of thousands or hundreds of thousands potential states inside the vehicle state graph. And so now the question is, how do we manage this? Because it would be way too expensive to download all the configurations. It takes too much network overhead and so on. And so our idea is to find a way to clusterize this graph so that, for example, if we merge states S4 and S5, then we generate one configuration for A1, 5, and 2 that run at the same time. And so, of course, the vehicle doesn't need to switch anymore between the two contexts. And actually, you can see that it could even be merged with S1 since it's already the definition of S4 and 5. Okay, so that's great. But if you need to clusterize, probably you have some objectives. And so how do we clusterize this graph? So that's the objectives we try to define then to solve to optimize this problem. And so we have three objectives. The first one is to minimize the number of generated configurations. So this limits the size to download and the number of configurations to store in the vehicle. You also minimize the frequency of reconfigurations, because if you introduce a lot of CPU overhead, if you switch too often between states. And then finally, since scheduling takes a lot of time, we also want to minimize the number of scheduler calls in the cloud. So the generation happens in the cloud and is pre-computed. We optimize all this, we clusterize the graph, and then everything is downloaded in the vehicle and ready to be switched depending on the context. And so to minimize all these objectives, we define a very simple objective functions, which is simply the sum of all the three objectives. And we'll see later that this is enough. We don't need weights or something complex. This is enough to show that we have achieved the minimization. So here's the approach we have. So we start from the same state graph in the beginning, and we use a combination of some methods. The first one being spectral embedding. So here we actually place each state in a n-dimensional space, and the position is going to be relative with other states depending on their probabilistic relationships. So for example, S4 and S5 switch very often together, and so they are close together. The next step is to create a tree that represents the relationships of probabilities between the states. And so we start from the smallest distance, S4 and S5, and we create a link here to show that it would be nice to cluster them together since the vehicle switches often. And we repeat it for all the distances. And now, if we think a little bit about how to generate these configurations, well, the idea thing you would want to have is to generate one configuration here. And so then you never switch and everything is beautiful. You have a static configuration, just like before. However, we suppose that the hardware capabilities are not enough. And so we're going to have to break up. And so if we notice that we go from top to bottom and we try again to schedule here and here separately, then we notice that objective functions can only increase. Because when you go down, you increase the number of configurations, then you have to switch between more states, and also you need to call schedulers again. And so we see that if we start from top to bottom and then stop as soon as we find something for each state, then we have finished and we have clusterized the graph with our objectives. And so here's some insights of what this could look like in a bit more realistic scenario. It's still very simplified. So we start by generating a hardware topology. And of course, this can change with every vehicle. So you have to run again with a different hardware topology. You also generate some applications. So we generated an app store of 500 applications, just as an insight of how this could look like. And then for each application, we generate random dependencies. And this will set some flows, network flows, that will be allocated allocated between the applications when they are active. And just as a simplification, we specify a random bandwidth requirement for each flow. So this just simplified just to demonstrate the concept. But of course, depending on the network scheduler you're going to choose, then the parameters can change. So if you have QoS requirements, latency, jitter, then everything depends on the scheduler you choose. We just took something pretty simple. And then the final piece you need is the vehicle state graph. So here's a matrix that shows a random Markov chain with one pixel being the transition probability between state A and state I and J. And then once we have this, you have the same thing as I showed you before, just with a little bit more points. So you start with the vehicle state graph. You embed it into a low dimensional space. I took 2 dimensions just for visualization. And then you generate the dendrogram. It's called dendrogram, the tree. And you start from top, you call the scheduler, you see if it's feasible and you have a valid configuration. If not, you start again at the lower layer. And at the end, if a state is green, then you can use a configuration that has been generated in the upper branch. If it's red, then you stay on one. You keep the generation for one single state. And so here's some insights of what performance we can expect from these different approaches. The first one is the static worst case. So it's traditional, what we had before. And so what we try to do is to select a random combination of apps to activate at once. And we try to find what is the maximum we could fit inside the architecture with the EE topology we selected. And so we saw that we could allocate a random combination of 28% of applications at most. And so this shows that with one single configuration, we cannot fit every application in the vehicle. So then what we tried is a second scenario. We took the vehicle state graph completely raw. We didn't change anything. And then for each state, we generate one configuration. So of course, everything is going to be valid. So every config is valid. However, you can see that the number of configurations is pretty high. The total frequency of reconfiguration and transition is also high. And the number of scheduler calls is relatively high. And once we apply our clustering method, then you can see that we have an improvement all 3 levels. And we ran again the same code with a SAT solver to make sure that it's exact and we get the same numbers. So we have minimized the objective function for this particular scenario. Great. So just to discuss a little bit what this looked like, let's talk a little bit about complexity, because of course it matters when you are a automotive OEM with hundreds of vehicle variants. So what we chose as a design for when choosing the algorithm is to first don't put too much of a priority on generating the initialization step. So when you have an app store, we can imagine that we do releases. And so we periodically run again an initialization. However, since we have a lot of vehicle variants, it should be relatively fast to generate the configurations for every vehicle and then deploy them in real life. And so this is why we have an initialization step that has a relatively high complexity. If you want to contribute and improve this, I would be glad you would. And so let's start the first approach, mainly because of the hierarchical clustering, because it has to sort the distances between every state. And then the iterative search has a lower complexity, which means that we can generate more easily configurations for every vehicle variant on the OEM. And if you are on an industrial scenario with some more real-life applications, you can do some small optimizations. The first one is that you can start at an intermediate level, because if you have a very cheap vehicle, you know that the very top features with everything included is not going to run. So you start lower to go faster. You also skip multiple levels at once. If you see that something is unfeasible, you go faster and you do sort of a dichotomy search. And then finally, since every branch is completely independent, you can evaluate them in parallel in the data center, pre-compute everything. And so this is relatively designed for a rolling fleet management where you have a lot of vehicles and you need to generate configurations for all of them. Do I have time? I do. So just as a quick summary of what the architecture looks like, you start with some inputs with the vehicle state graph we just defined. You define one hardware topology for one particular vehicle, and then you define the app store with flows, dependencies, and so on. Finally, we use this state orchestrator, which is basically our clustering algorithm, and we iteratively call the scheduler to generate the configurations. Once it's ready, you download them to the vehicle, and then it's going to simply select from the pre-computed and stored configurations the one that needs to be active based on what the user wants, if he wants to launch Netflix or give priority to ADAS functions instead, and so on. So he basically chooses and the vehicle applies. Okay, so as a conclusion, there are some advantages and there is one major limitation. The advantages is that in an industrial scenario, we believe that it's a relatively reasonable approach because we can skip steps and evaluate in parallel, so it's fast enough for regular releases. We can extend the vehicle capabilities, and so now OEMs have two choices. They can make smaller vehicles which keep the same applications with smaller hardware, which is more sustainable, and I prefer this way. But then also they can keep the same hardware and extend the vehicle with more applications and features. And so this is completely automated and can be deployed pretty easily, and it still maintains all the guarantees and the QoS requirements from the network flows. However, there are two limitations. The one is that there is a new concept, and then engineers need to maintain this new vehicle state graph, which can be generated, but there's also some work to do. And also, since every configuration is treated completely independently, you cannot reconfigure while the vehicle is driving, because you have maybe buffer usages that may be different. You haven't predicted what's going to happen. And so, of course, it's limited. And so with the state of this work, we think there are still some pretty useful use cases. The first one is to extend the vehicle or to make smaller vehicles, of course. And the second one is probably shared vehicles, because you could have a subscription where you put more features towards ADAS or infotainment and so on. And then the vehicle with some common hardware, it can activate different features. So as long as it's parked and it's not really active, you can reconfigure the network. And so that's a potential use case. And as a future work, we'd like to evaluate performance with more realistic network QoS flows with deadlines and latencies, even though it shouldn't really change the methodology. We would like to extend this with maybe some onboard components that can optimize further for best effort applications and so on. And finally, it could be interesting to use this method to reduce the energy consumption because you're using lower hardware. Or maybe if you clusterize differently, you can choose if you want to clusterize more and have larger configurations or smaller configurations with less hardware. And so that's a trade-off that could be interesting to study. And so there you have it. Thank you for attending. And if you have any questions, I'm happy to answer.
I have a question what you showed us the future work thing TSN and scaling is a very large problem in the automotive industry because you use a common even state or multiple functions.
Yeah.
So do you validate your approach right now? Because you can always, of course, mix a lot of apps and then assume that they have some data rate, but the problem is does the motor still start or is your brake working at the exact moment?
Yes.
So
okay.
You use the same cable and get all these issues.
Yeah, for sure. This work is focused on the, let's say, fleet management layer. So we have your very high layer. And then we dedicate, when I call network scheduler, what I really mean is some component that's going to generate the configuration and also validate, make sure that the system integration is correct, that the vehicle is in a correct state to be run at. And then, so we basically offload this to the other component.
Because I could imagine that if you put 500 apps in your vehicle, a lot of them will not work on the same table because you also have some functions. What this methodology allows to do is that we have a vehicle state graph that's very general, and then we're going to clusterize the most we can. But if there is one state which has a lot of application,
then where the algorithm is going to choose to like keep the state single. And so it's still allocatable. And so what we're doing here is to search to minimize the objectives, but still retain valid configurations. So they are still, I mean, they can still be shared inside the Ethernet cable. So it still fits.
Maybe we should end this up with the 3 positives.